Okay, now I want to go through a couple problems involving limits. So here we go, because there are a ton of special cases here. I will say this is going to definitely be overkill. You're only going to be looking at a couple problems, most likely on the exam that involve limits, but this kind of will cover everything that you could possibly need to know. So here we go. First one, you can see that we do have a piecewise function, which is nice to readdress. And anytime that we're dealing with a limit problem, we want to see if we can use direct substitution first and foremost. So here you can see that we're approaching 2 from the left. Here in letter B, -4 from the right. So this is just a one-sided limit. So if we're going to approach 2 from the left, we would be in this interval here, this middle function or piece of the function is what we would use, because we would be approaching 2 from here. And then all we have to do is just utilize direct substitution. So we plug in 2. So we'd have 2 squared minus 5. Evaluate that, you get negative. We would be in the same piece if we were approaching -4 from the right, because if we're at -4 here, approaching it from the right would lead us, we would be in this interval in the middle there. So we would use the same piece. So if we plug in -4 to that, you can see we get 11. So a little review of one-sided limits, piecewise, and direct substitution. Some more that involve direct substitution. This one right here, number 1, very straightforward. You always want to just try to plug things in and see if it works. So here you plug in 2, you evaluate that, you get -2, life is good. Okay. But when we come across some scenarios here where we may not be able to do that. For instance, in this case where we approach 1, we can see that if we plug in 1 to that denominator, we would get 0, and that would be an issue. So with this one, we can go ahead and try to factor, but nothing simplifies. So one way that we can express this is we could say that that limit does not exist, because there's no way that we can get rid of this x minus 1. So there would be a vertical asymptote here. Now we will run into some problems later where we will have vertical asymptotes, and we can see how we can deal with those. But here, this one doesn't simplify. So a possibility is to say that it does not exist. 10 is similar, where we can go ahead and factor, but you can see that the difference is this x minus 8. Those cancel out. So then that puts us in a situation where we can use direct substitution. So we plug in 8, we get 18, and we're done. With 10, though, we could also use L'Hopital's. And L'Hopital's, remember, if you get an indeterminate form, which means you either get 0 over 0 or infinity over infinity, you can take the derivative of both numerator and denominator and keep doing that until you can utilize direct substitution. So in this case, we only had to do that once. So if I take the derivative of the numerator here, I'd have 2x plus 2. The denominator just becomes 1. And if you plug in 8, you'll get 18. We could not use L'Hopital's here in number 4, because if you plug in 1 to the numerator, you do not get 0. So you don't get a case where it's 0 over 0. So that's why you can't use L'Hopital's in number 4. Sometimes with limits, we have special rules. So there were some ones that we utilize. This is probably one of the more common ones. When you are approaching 0 and you have the sign of a number times x, that could be 1, that could be 3, 2/3, whatever, it could be anything. And then over x times a constant, it works out. The shortcut for this is just to recognize that and know that it's just going to be a ratio of those values. So 2/3 is your answer there. So if this was like the sign of 5x over 6x, your answer would be 5/6. Okay. Another algebraic approach that we took with limits was multiplying by the conjugate. So you could see here, to kind of simplify this, there's the issue again with the x being in the denominator, that going to 0 would be a problem. So we can multiply by the conjugate. I'm not going to talk much about that algebra that goes into simplifying this, but you can follow through there. Just recognizing that you need to multiply by the conjugate there is an important component. When you have the problems that involve a fraction within a fraction, those obviously can be a little bit challenging, but here, the way that you can get rid of this situation where you have a fraction in the numerator is to multiply by the least common multiple. So the least common multiple amongst this right here would be 3 times x plus 3. And when you multiply that through, it simplifies down pretty nicely, and we end up able to cancel these x's, which allows us to now utilize direct substitution. Okay. Vertical asymptote situation. So this is similar to the one that we saw before. And we could actually see where we're approaching. So sometimes both may be approaching vertical asymptote where we'd be able to see that it's approaching infinity. Other times, one end might be approached from a vertical asymptote. We might be approaching positive infinity one way and negative infinity the other. In that case, we would say that there's no limit or the limit doesn't exist. So in this case, for something like number 9, you can see it's a one-sided situation within this. So for us, what that means is we just have to test this from the right. So to the right of 1. So I'm going to pick a value that's really, really close to 1 and plug it in. So 1.00001. If this was approaching 1 from the left, I would pick something really close to 1 on the left side of it, which would be 0.9999. Okay. So we plug those values in, and what we end up getting is 1.00001 squared is going to get closer and closer. It's going to be 1. And then if we do this arithmetic in the denominator, we get something that's really, really small. Well, if you have a constant divided by something really, really small, that would eventually go to infinity, because this is just going to continue to get smaller and smaller the closer and closer you get to 1. So when we divide by something really small, we go to infinity. We divide by something really large, we go to 0. So keep that in mind. So here with number 12 and 14, these are examples where we're approaching a value from, we'd have to look at it from both sides, because in order for a limit to exist, it has to approach the same value from the left and right side. So we have to evaluate this in number 12, approaching -2 from both the left and from the right. So -2 from the left with this scenario where we have a vertical asymptote here at -2, we would go ahead and plug in -2.001. Okay, that's the left of, like, close to -2, but on the left side of it. On the right side of it, we would use -1.999. Okay. So if you look at these situations, like in this numerator, I have 0.9999. That's going to get closer and closer to 1. And then down here with this multiplication, this is going to be something really small. So we have something that's getting close to 1 over something that's super duper duper small, and will continue to get smaller as you do that multiplication and get closer and closer to -2. So this value divided by something really, really small, since these are both negative, it becomes positive. So you're dividing by something really, really small that's positive. We'll go to infinity. -2 from the right, same kind of deal here. Again, this is going to give us something very, very small down here. So we have that 1.001 divided by something smaller than it. That will go to infinity. So since both of these are approaching infinity, we say that the limit, another way we can state that is that the limit approaches infinity. So this is a little bit more specific than what we did in that first example, the first slide, okay, or second slide, sorry. Same kind of thing here with 14. The thing that I just want to emphasize is, since these do not mesh, we would say that the limit doesn't exist, or that there's no limit. Sometimes we just need to think about what type of function we are dealing with, right? So here in this case for 28 and 13, these are trig functions, and those are their waves, right? Sine and cosine are waves. So what's happening here with this one is just kind of amplifying that wave a little bit, so it actually make it kind of go a little bit crazier, like a bigger amplitude as time goes on. The amplitude would increase. So that's just going to be oscillating, and it's not going to approach a specific value as you go to infinity. Here, the amplitude remains the same, but again, it's still just cycling through, and there's no consistent value that you're going to be approaching as you get bigger and bigger. So it's going to continue to follow that wave-like pattern. So you just got to know, you got to think about what the function is and know that that would be a scenario where the limit does not exist. Other times we have to take into consideration which function has more power, or which one will like increase faster, or again, like overpower the other. So like in this one with the 2 to the -x, we can kick that down to the denominator. And this is exponential. So exponential is going to grow faster than this quadratic, right? So power functions do not grow as fast as exponentials. So in this case, you have a value over something that's bigger, right? So you got a value divided by something that's going to be really, really, really big. That's going to get closer and closer to 0. Okay. With 11, same kind of deal, just in pieces here. So even this is x to the 7th, it will increase faster, but the exponential still going to grow faster than that power function. So in this scenario, again, this is going to overpower it. You'll have something, you'll have a value up here, but this will be much bigger as you get closer and closer to infinity. So again, big value in the denominator. We'll get closer and closer to 0. So that portion gives us 0, and then that just stays as -5 or -5 to give us -5. Okay, a little bit of review of some algebra 2 here in number 8, when we're looking at when you have a polynomial in numerator and denominator. With that case, you can compare the degrees. What we would encourage you to do is compare degrees. So this has a degree of 1, this has a degree of 2. The degree of the numerator is smaller than the degree of the denominator. You'll have a horizontal asymptote at y equals 0. So if we're sending this thing to infinity, horizontal asymptotes do measure end behavior. So if we go forever to the right, we're going to get closer and closer to 0. So the horizontal asymptote just becomes that limit. Same thing going on here with number 19, but a different rule, polynomial over polynomial, but the degrees are both 4. So our rule for horizontal asymptotes is if the degrees are the same, the horizontal asymptote will be a ratio of the leading coefficients. So in the numerator, the leading coefficient is -1, and the denominator it's 5. So this would be -1/5 for the horizontal asymptote. And again, we're sending that to infinity. So if we're sending that thing to infinity, as we go forever to the right, we're going to get closer and closer to that horizontal asymptote of -1/5. Be careful with these types because something like 23, you can see that the numerator is not written in standard form. So both of these have a degree of 7. So degree of numerator and denominator there in 23 are both 7. So you just do -5 over 1. So that's going to be your limit there as you approach negative infinity. So even though it's approaching negative infinity, it's still going to, again, have that same behavior where it's going to get to -5. Okay. And then here in number 9, we can kind of break this up and do the limits individually. So we follow the same rule over here, same degree, ratio of leading coefficients. So that's going to be -6 over 3, which is -2. This becomes 0 again because we're sending x to infinity. So 1 over 0 will get closer and closer to 0. So the sign of 0 is 0. So you have 0 minus 6 over 3, which is -2. That is all. I hope that was helpful for you in regards to a review of limits.